Hi, everyone. I'm Tegan Brennan, a PhD candidate from the University of California, Santa Barbara. Today, I'll be presenting my work with Shamanta Saha and Tafik Bolton on JVM fuzzing for side channel detection. Side channel vulnerabilities in software are caused by an observable imbalance in resource usage across different program paths. Most side channel analysis tools aimed at detecting or quantifying side channels in software consider the source code of the program to be the sole determiner of a side channel vulnerability. However, this is not the case. Just-in-time or JIT compilation can introduce timing side channels even into programs where paths appear to be balanced at the source code level. Here, we have an example of a seemingly balanced equals function, where the same amount of work is done regardless of whether the characters of the two strings being compared match. The two sets of violin plots below show the change in behavior of this function with and without enabling just-in-time compilation. On the left, we see that when JIT is disabled, the execution time behavior of this program, when the first pair of characters match, is indistinguishable from that when the first pair of characters do not match. No side channel appears to be present. This story completely changes when JIT is enabled. Now, the two timing distributions are separable and a side channel in time has arisen. The cause of this side channel is an imbalance in the input distribution to the program. We choose input to the program randomly, and there are more strings whose first character does not match that of the stored password than those whose does. At present, there is no side channel analysis tool capable of detecting these JIT-based side channels. In our work, we present a two-stepped approach to inducing and evaluating JIT-based side channels. The first phase is an input generation phase, where we generate priming and test input. The priming input is the input used to prime the runtime to favor certain program behaviors. We generate priming input using the fuzzer AFL in order to cover many program behaviors. We use a combination of dependency analysis, program instrumentation, and pattern matching to generate sets of evaluating input pairs, which we use to determine if there is a side channel in time in the primed runtime. If the pairs of evaluating input can be separated reliably by their execution time behavior, then a side channel is present. Here, we show our process to generate evaluating input. We create an instrumented version of the program under test that returns a tuple representing the behavior of the program at branches and loops. Any loop or branch condition that is secret dependent is marked as such. We then partition these tuples into pairs based on pattern matching with the goal of finding partitions of input that differ on secret related branches but agree as much as possible elsewhere. We use these as our evaluating input. In the second phase, we prime the Java runtime in favor of each priming input in turn. Then, for each priming value, we evaluate whether the resulting runtime state has a side channel through which the sets of evaluating input are separable. We evaluated our automated technique on three benchmarks widely used for side channel analysis: the Blazor, Themis, and difffuzz benchmarks. These benchmarks consist of two sets of programs: the original programs containing a side channel vulnerability and their fixed variants. We experimented on both sets, but I show our results on the safe variants here. Even though past side channel detection tools have deemed these programs safe, we are able to induce JIT-based side channels in the majority of them with our automated technique. For the Blazor dataset, we were able to automatically induce a JIT-based side channel in 13 of the 14 safe variants, a result which directly contradicts that of 4 different side channel analysis tools. Thank you for coming to our poster presentation, and please reach out with any questions.